Okay, so hello everybody. Welcome to machine learning class, and let's start with some introduction. Let's look at the syllabus. So the the main page for the class will be this GitHub ML GitHub account where you will find lecture notes and information for each week. So for example, today is week 1, and here you will see the problem solvings, homework assignments. So all the materials will be published here. And the link is on my courses. So in this class, there are 12 homeworks, but the homework with lowest grade is dropped, so it's 11. So you can skip one homework without penalties. Then we have two parts. One part is the machine learning before deep learning. So it's approximately until the break. And after gradient boosting, we will move to neural networks. In the end of the first part, there is a midterm, but it will be take home just to save the lecture time. And in the end, there is no final exam, there is final project. So final project, I will give you 2 projects to choose from, but if you want to work on your own ideas, you're welcome to. Just let me know what you're interested in. The project will be on the images, but if you're interested in audio processing or text processing, so you can work on your own project as well. And the grade contains these four components: homeworks, midterm, final project, and 10% is the problem solvings or participation during class. Um, the late penalties are 80%. So for example, every day it's multiplied by 0.8. So the first date, the late submission will be graded with cap 80%. The second day, it will be 8 times 8, so it will be maximum 64%. And for example, 5 days later, it will be like how 50%. And typically, we will have a homework assignment, then on 1 week, then you have next week to do this homework assignment, and on Monday after the second week, it's the date due. So typically, you will have like current week, next week, and you should return on Monday of the following week. Okay, so I won't start with definition of machine learning. We will give definition of this in when we will go to deep learning because deep learning is the part of machine learning, and then we will be prepared for definition. But today we have two topics to cover. One is called similarity hypothesis, and the second one is k-nearest neighbors. So that's why you have two problem solvings, 1 and 2. And I will start with some introduction and history. So during World War II, in Germany, the first flying bomb was developed. And the reason was because they couldn't um, um, invade Great Britain because of the sea. So they, in 1944, created these flying bombs that could actually destroy the Great Britain. And it was kind of the end of this World War II, 1944. Um, um, in MIT library, Norbert Wiener, who is the person who coined the word cybernetics. Cybernetics is the science about living organisms and machines, which later transformed into AI and currently in machine learning, ML. So it's well-known Lincoln laboratory, which works on radars. They created a first radar station that could calculate the coordinates where the anti-missiles should fire to hit these bombs. So this was the first machine learning system that actually could make predictions just from the data, from coordinates of the incoming missiles, for example. Because before that, engineers had to calculate the trajectory, and it took time. So, well, while you calculating the trajectory, maybe 100 bombs will hit you. So the machines helped to do this automatically. And here's how this laboratory looked like. So these radars. But in the same year, Germans introduced a new missile. So the first one called V1, V1. The second is called V2. You will see that a little bit later. It looks like a modern rocket. So it looks like this. Unfortunately, there was no, and there is not even now a good system that can hit this ballistic missile because it drops from very high altitude and it drops with very high speed. So it's very hard just to hit it. And nowadays you can see these images in real time in the war with Ukraine. Like I'm from Russia, I'm Russian, but Of course, I don't support this war. And several weeks ago, Russia actually launched the ballistic missile on Kiev, and um, it wasn't, even though there are many defense systems, Patriots and Iris and so on, but of course they couldn't hit this ballistic missile. But the good thing about this is that we can predict actually where these ballistic missiles were launched, where they were fired. And in 1960s, if you've heard about algorithm fast Fourier transform, FFT algorithm, sometimes students just studied this in algorithm class. So this algorithm helps to calculate efficiently the position of the starting point. And this is where the nuclear war actually stopped. Because if you can calculate the position of the launching of the bomb while it's flying in your side, you can launch the bomb in the same position. So after that, this competition actually stopped because, well, you can fire a bomb, but you will get the bomb as well. So there's no reason to launch. So, okay, this is the short introduction. Now let's talk about our first. Oh, I didn't mention about the textbook. Uh, so I'm not using slides. So you're welcome to open the textbook, which is on lecture notes, which is on GitHub. Here's lecture notes, and maybe it will be easier to follow. But I will write just on the screen. So, but I will open the lecture notes because there are some pictures. Let's start with first topic for today, similarity hypothesis. So, let's look at these pictures. One picture represents a fir tree, another picture represents a pine tree. And we will refer to these pictures as training data. Now I will show you another picture and ask you to detect if it's to classify if it's a fir tree or a pine tree. So what do you think, looking at these pictures? The fir tree is the left for you and pine to the right. How would you classify this new image? Fir tree. Or how did you decide that it is a fir tree?
A similar shape in the just that structure of the branches of like the leaves that has a good cone shape.
Um, well, maybe form, yes, like this cone form. What we call these features, the attributes that we use or use to compare some data, we will call features. So one feature is the shape. Can you maybe think about other cues? So maybe you can see trunk here, and you can see trunk for the pine tree, so less dense greenery. Maybe some other cues. Of course, our brain does it automatically, but if we want to teach machine to detect, we should um, provide more instructions to machines. Um, so, okay, what I have here trunk, dense greenery, color, and based on these features, we compare the new data with our train data and make the decision. So this is called the similarity hypothesis. We will classify the objects uh, with similar features to the same classes. So typically, I will use the notation x with superscript for the data point, and the lower subscript will stand for the feature. For example, um, x1 will stand for if the trunk is visible or not. X2 will stand for the shape, for example. And that's why I will use subscripts, um, oh, sorry, superscripts for to label the data point. Just it will be easier to use. So n is not a good index. Let's call dimension d, and the n will be the number of data points, like the number of images, for example. In our case, it was two, just two images, but in general, we can have hundreds, thousands, millions, billions of images. So, and we will classify different data points by closeness. To define closeness, we need to define the notion of distance. And we will use three distances in our class, mainly. Um, the first distance will be Euclidean distance, or um, often we will refer to this as L2 distance, L2 norm. So Euclidean distance is defined, for example, if we had just two features, it's defined as the absolute value of this difference of x1 and x2. But more often you will see this notation like double lines, and just to show that we use L2 norm. There are also are the indices, and it's defined as the square root s squared t of the squared differences of components. So just standard Euclidean distance. So we take the first component difference plus the second. If there are more components, we just continue our summation. So the second distance will be, and here's the illustration. So the Euclidean distance is just the normal distance between 2 points. The second distance is called Manhattan distance, and we will refer also to it as L1 norm. L1. Oh, yeah. So if we use double lines, it's called the norm of vector. So I will use this names interchangeably, but there's a little bit difference. The norm is the distance to the origin, but if we take the difference, then the origin will cancel out. So that's why we use for difference we use interchangeably distance or norm of the vector. So it's defined as subscript 1, just as the absolute values of differences of components, like the difference between first components plus the difference between second components. So if we have 2 points, x1 and x2, then the first Euclidean distance will be just a straight line. If we use Manhattan distance, and you will understand now why it's called Manhattan distance or L1 distance between 2 points, then the first step is to take the difference of the first components. So I take the difference between x1 of the first point and x1 of the second point. So this is this distance. And then I add the distance between second y component. So then I should add this distance. The sum of these lines will represent L1 norm. And if we look at illustration, could you answer the question, which of the lines, blue, yellow, or red, we don't take into account this green light? Of course, the green light is the shortest path. Which line is longer? I mean, all except the diagonal. Yeah.
No, nothing.
Yes, they're all the same. Why they're the same?
It's you put the same number of edges of squares in change.
In any, yes, in any direction, if you sum up the horizontal lines, they all will sum up to this side of the square. And because of the um, Manhattan streets, it's called Manhattan distance because of blocks. It doesn't matter which way you will choose from point A to point B, it will be the same distance. So it's L1 distance. It's not distance. The last metric that we will use is called um, mhm. What is the name of this guy? Sorry, I have forgotten. Hamming distance. So it's sometimes used in coding. So Hamming distance, typically we use another name, 0, 1 loss, but when we will introduce loss function, then we will call it 0, 1 loss. Hamming distance is defined as follows. It's 0 if x1 and x2 coincide, and it's 1 if the points are different. So I will use so-called Everson brackets. Everson brackets means that it's 1 if the statement is true. For example, here I will write x1 equals x2. So if my points coincide, then this statement is true. And the result of this bracket should be 1. But I want to have distance 0 for the same points. So I will change this to not equal. And then it will be 0 if the statement is false. And the statement is false when actually x1 equals x2. And it will be 1 if our points are different. So if the statement is true, they don't coincide, then we return 1. So if we want to define the distance between points x1 and x2, if they are different points, the distance will be always 1. Doesn't matter how far our points, if they don't coincide, we will say distance 1. And this distance will work, for example, for not numerical data. For example, 2 colors, yellow and red. How to find the distance between 2 colors? Just if they're the same, we say that distance is 0. If they're different, we say that distance is 1. And this brings us to the types of features. So let's talk about data types. So data types. I will just bring it up. So the features can be Boolean or binary. For example, true or false. If, for example, there is a a day off or it's a working day, and so many other examples. Another type of feature is just numerical, and of course, machines work only with numerical features, only with numbers, like temperature, some indices, and so on. The other type of features is categorical, and this class has two subclasses, nominal and ordinal. So if you think about colors, um, can we can we order the colors, like sort them? We can maybe if we think about frequency of colors, like it's physics, but in general, we can't um, say that yellow is greater than red. So this type of features that are different and not numerical, but we can't compare them, are called nominal. Another example of nominal features are names of the cities. Of course, we have our own preferences. We can uh, prefer one city to another city, but for algorithms, typically we just want some indexing of these cities. So it's example of nominal data or names. Um, let's think about other data. For example, they are not numerical, but we can order them. Can you think about example of this data, which are not numbers, but we can somehow sort them? This data will be called ordinal. Yes?
Sizes of clothing.
Oh, you mean size by letters, because there's size by numbers. But
Like
but if the size by letters, it's a good example, like ML. We can't compare number letters, but we can definitely order them. Yeah, you have. Okay, so the next example of data types is time, for example, um, position, and this uh, all corresponds to so-called table data. Then we have non-table data, which are images, texts, audio, and typically classical machine learning before neural networks works with table data. And for non-table data, neural networks do better job. Okay, so now let's do the first problem. The first problem, you have um, made up information about trips in Uber or Lyft, and the information about if the person agreed to um, upgrade the trip or not. And in problem two, we have a new user, and we should predict based on this similarity principle if this new user will agree to upgrade or not. And in problem three, I changed just one number, just 100 will be, so you will need to recalculate only one line. And I will help start up with so we will use Manhattan distance because it's easier to calculate. You don't need to take squares, square roots, just the absolute differences. So for problem 2, okay, so for problem 2, you will need to calculate two distances. The distance 1 will be the distance between the first line and the new record. And distance 2 will be the distance between second line and the new data point. And then based on, oh, you need the so I didn't mention that we will have two kinds of problem solving, coding and written. So the paperwork is due the end of class. The coding, so next time we will have coding problems. So bring your laptops, but because I understand that not everybody can bring laptops, the coding problems are due the end of the day of the class. So did somebody calculate these distances, D1 and D2? What are the values? Yeah.
I have the first one. I believe it should be 23 if I did addition correctly.
23. Yeah, it sounds correct. And D2?
I haven't.
Yeah. Did somebody calculate it?
I got 35.
Okay. If somebody will get 35, then it's correct. And which answer will be for this new user? Will he agree to upgrade or not?
I also got 35.
Oh, great.
So then you would agree because the distance is lower for the one that agrees.
Yes, based on this principle, that the distance between features is smaller, we will answer yes. What about the problem 3? It's just easy to understand that the first distance will be huge because there is one number 100. So the answer will be different for problem 3. And let's think if it's reasonable. If it's a reasonable answer. So the new user, we don't have any information about new user. So this column, how often the premium was used, it will be always 0 for the new user. So if we compare this column, this feature, how often the premium was used, this feature, this difference will be always so in problem 3 it will be 100. But is it reasonable to compare the data that we don't have information about for the new user? So what are the possible solutions to fix it? So one solution, you can just drop this code and don't take into consideration this feature because it's not informative for the new user. Another way is to consider to introduce weights. So you can introduce here the numbers alpha 1, alpha 2, alpha 3, alpha 4. And for example, if we think that this feature is not important, we can use this alpha equals, for example, 0.1. And if the difference is 100, it will be multiplied by 0.1, and the total result will be just 10. So we will kind of reduce the importance of this feature. If we think that age is important feature, maybe people of the same age, well, but of course we should also include income, use with the same frequency Uber, then maybe we can assign this weight to 100. So this is another way to add weights to our features. So let's talk about our data. So typically we will have train data or training data. In our case, we had just two lines of training data, and training data is a pair of features and targets. In our case, the target was yes or no. And we will have n data points. The space of features we will use, we will denote as X capital, and the space of targets we will denote as Y capital. So, for example, in our case, with trips, the target space contained two elements, yes, no. And X was four-dimensional vector with features. And then the goal of machine learning is to come up with algorithm. So I will use A for this, and we will call this model. The algorithm that for a given data point produces the prediction. And typically we will use ypred or yhat for prediction. And the goal of our training of our algorithm to make the prediction as close as possible to true data. So this is the main idea of machine learning, to find a model or algorithm that for given features will predict the target. Well, it's called supervised learning, but we will work mostly with supervised learning. In unsupervised learning, we don't have targets, we just work with features like clusterization, dimensionality reduction, and we will have 1 week on dimensionality on unsupervised learning. So this is the goal. The goal to come up with algorithm that will provide predictions, and ideally predictions should coincide with true values. And sometimes, not sometimes, but most of the times, we even don't know the true values. For example, like for this new user, we just want to make a prediction. And to evaluate the quality, we should introduce one more notion, which is called loss function. For example, if you make incorrect predictions, you can lose money. That's why it's called loss function. So loss function will measure the distance between target and prediction of this target. And this function will map the cross product of targets. So it will map this into a number, but not negative number. So this is loss function is defined on the on targets, but one target is true, another is the prediction, and it's not non-negative, and it should satisfy only one condition. The loss is 0 when our prediction is equal to the target. So if our prediction is 100% correct, then the loss is 0. So just one condition, loss between y and y hat is 0, if and only if y hat actually the same as the target. Typically, we use L2 loss function, just the sum of square differences, or L1 loss function, the sum of absolute values of differences of coordinates. In classification, we use so-called 0-1 loss, which is the sum of correct predictions. Because you remember, if our points coincide, then this Everson bracket returns 1, and if they don't coincide, it returns 0. So we can introduce the measure of quality for classification accuracy as the number of correct predictions over the total number of points. So, but if I use this notation of these Everson brackets, it will be so if it equals, then it returns 0. If it's not equal, if it returns 1. So if my prediction is correct, then the statement will be false. If y hat coincides with y, then this statement is false, and this bracket returns 1. Does it make sense? So it will count actually the number of correct predictions over total number of points. So it equals to the number of correct guesses over the total number of points. So when I told you that the accuracy of this anti-missile system was 90%, it means that if we calculate the number when the system actually worked efficiently and divide by the number of total use of the system, it will be 0.9. So this is the definition of accuracy. And now we're ready to go to our first machine learning algorithm, which is called k-nearest neighbors. So the first algorithm. So in this class, we will learn, I believe, hundreds of different algorithms, machine learning algorithms. So the first algorithm is called k-nearest neighbors. Of course, we will learn the most used algorithms. Nearest neighbors. That's why I decided to skip midterm, because I want to introduce as much as possible material to cover more topics. So let's look at this one example. So typically we have multidimensional features. Like for the trip, we had 4 features, but in real life, the number of features is more than 100 is normal situation. But if the number of features is just 2, then we can represent these features on the plane. So in this case, we have 2 features. You can think about like the um, the grade of the student and GPA, 2 features, and we want to predict this if the student will actually finish the school or will drop. So just 2 features. And in this case, we can, of course, it's not GPA because negative numbers and not the plus. Are you in -1 class? No. So, but just to give you an idea, that if we have 2 features, we can visualize. If we have more features, we will use dimensionality reduction techniques that will reduce the number of features, and then we can visualize them. But we will talk about dimensionality reduction after the supervised learning, right before neural networks, during the midterm week. So, and now we have new points. New point has features, but we need to predict the class. So how would you classify the red point? As brown class or blue one? You can just speak up, without brown. How we would classify the blue point? And what about black point? So let's think about how you classified the first point. Why did you decide that it's a brown?
Most of what's around is brown.
What is the name of our current topic?
Neighbors.
So we look at the neighbors. You're right. So if we look at the neighbors of this point, most of the neighbors are brown. If we look at the neighbors of black points, it depends on what size of our neighborhood we will choose. If we choose a small one neighbor, maybe it will be blue. If we will choose a larger neighborhood, maybe we will have more brown points in this neighborhood. And this is actually the idea of this algorithm. So let's look at a more precise example. So if we can see, in this case, we have blue squares and red triangles. If we consider just 3 neighbors, and neighbors, why we talk about distance, we sort our points based on the distance. So for example, from this point, the nearest point will be this one, then second nearest that one. So we take 3 nearest points, and then we make the classification. So how we will classify green point in case of 3 neighbors as triangles or squares? Triangles, because we have more classes of red triangles. But if we look at the larger number of points, like 5, how we would classify this green point in this case? As blue squares. So the k is a hyperparameter. You will hear some often about parameters of the model and hyperparameters of the model. So hyperparameters are something that we choose like independently on the model itself. Parameters will tune the model. So k is a hyperparameter. And next time we will talk about how to choose actually the best k. But today, just important to understand that you should choose it in advance beforehand. So here's the algorithm. We have features, we have targets, and not necessarily just 2 classes, maybe C classes. And the training is just to memorize the data points. The next step is to calculate the distances from a new point to every point in our data set. And then sort these points in this increasing order of these distances. So this double indexing means that, let's look at the example. So for example, in data set, my points had these indices, 1, 2, 3, 4, 5, 6, 7. But then I sort these indices by distance. So the first index, I1, will be 8. The second index, I2, will be 9. So it's kind of reindexing. And when we reindex our points, then we calculate, let's first look at the example, then you will understand the formula. We calculate this value. So, for example, I calculate the distance, the sum of distances to these points. And as you remember, my points 8 and 9 were red. So I count if my point with index 8 is blue. No, it's not blue. So this will be false and the result will be 0. If the next point is blue, no, it's red. So again, result will be 0. And the third point is blue, so it's 1, and the total sum will be 1. So I just count how many points of this class we have in the neighborhood of my point. So we have only 1 blue point in this neighborhood. Then we calculate the same sum for triangles. So this first 2 will be 1s, and this last will be 0. And the total sum will be 2. In other words, it's just 2 points, 2 red points in the neighborhood. And then we calculate the maximum. The maximum will be given by red class. So if we take argmax, the prediction will be red class. In other words, we just make the prediction based on majority of the points in the neighborhood. Okay, let's do our last. So this is the final formula. That algorithm, our A, is the argmax over all classes. And here we just sum how many points of each class we have. So let's do the last problem. And because we have There's 7 minutes left. I will help you. So let's do this together. So the last problem is will show you that it's not a good idea to choose even number of neighbors. So in practice, in k-nearest neighbors, we choose k odd, 3, 5, 7, and so on. Because if we choose, as in this example, 2, then we may have 2 neighbors with different classes, and it's hard to make the decision then. So in this problem, I ask you if the distances are the same, but classes, no, sorry, if the classes are different, then make a prediction by the the closer distance. So let's write down data. So the first step, I will sort the data by on my real line. So by feature, x is a feature. The smallest will be negative 0.5. The next will be negative 0.1. The next will be 0. The next 0.3. The next 0.45 and 0.7 and 2. So the predictions were -1, -1. For 0, it was +1. For 0.3 was +1. 0.45 +1. For 7, -1. And for 2, +1. So now I want to predict, so I want to calculate y hat based on, so for example, for the first point, we assume that first point doesn't have the prediction, and we want to predict the class. So I look at the neighbors, and the neighbors for these points are these 2. So the distance here is 0.4, the distance here is 0.5. They have different classes. Again, you will never run in this problem if you choose odd number of neighbors. But in this case, we will choose the class based on the smaller distance. The smaller distance is 0.4, so the prediction will be -1. Then we take the second point. The neighbors, it's a little bit tricky because the distance from here to here is the same as the distance from here to here. But anyways, the smaller distance is to the class +1, so we will predict this point as +1. The 0 is close to these points, and because 0 is closer to -0.1 than to than 0.3, we will predict 0 as -1. 0.3 is a good guy. It has 2 positive classes, so no problems. Positive class. The next one has 2 different neighbors, but it's closer to 0.3, so prediction will be positive. And 0.7 has 2 positive neighbors, so prediction is positive. Number 2 has neighbor with negative class, so prediction will be -1. So this is how we do classification. Final step, accuracy of our model. The total number of points, 7. How many correct guesses? 1, 2, 3. So the accuracy will be 3/7. So please leave your papers on the desks. I will collect them after you leave the class. And see you in 2 days.